This is an overview video of the material that I will be discussing in future videos on detailed database design. The major sources for this, I have the material on normalization and also section 8.1. In these videos, I will not break down the particular sections on that. It's just the notes on normalization, and if you read through as you go along, you'll see the match. The purpose of this overview is to review briefly the different techniques for detailed database design, starting first of all with what are the requirements for a good relational database design, and then what are the different components, and I will be describing those here. First of all, the requirements. Okay, we have dealt with high-level design. High-level design is primarily handled using entity relationship models and then using the rules to transform the entity relationship model into a relational model, which can be implemented on an RDBMS. We are now concerned with detailed design. What is the requirement? The requirement is one. Reduce the possibility of error. This is entirely and exclusively the purpose of detailed design. There is subject to performance issues. It may be the case that there will be trade-offs on performance issues in which error versus performance costs are such that we favor reducing the performance cost and tolerating some greater possibility of error. But in general, we will be focusing on reducing the possibility of error. This is frequently confused, including in the textbook, with the idea of avoiding duplication. Now, duplication can be a source of error. It is a source of error. It is not the only source of error, which is a key point, not the sole source of error. I would argue it's probably not even the major source of error. More to the point, duplication per se is not the problem. It occurs all over the place. It occurs whenever we have a foreign key relationship. It occurs, in fact, in order to reduce the possibility of error, we are going to create duplication. There are cases, notably in the form of attribute lists, where 100% of what we are producing will be duplication. The problem is unstructured duplication, and even there may be a trade-off. So again, this is the focus of all of detailed design, subject to performance trade-offs. Error within tuples. So let's consider a relation, and this comes from the textbook. We have a section with a course ID, section ID, semester, year, building, room number, which identify course offerings. Well, what if our course ID, and we can imagine we have ECE 656, section 001, so ECE 656, Section 1, semester, fall 20, year 2020, building, and let's imagine we were taking place in a building in E7, and the room number is E75343. So, what if ECE is incorrect? This will probably be a foreign key reference, but the point is there'll be a course table, a course relation in which it's identified as an ECE course, but we also have within that course code ECE. The semester, typically identified as FW and S, followed by the 2-digit year code. What if the year doesn't match? Room number identifies a building and a room. Not much use to you to have What room are we in? We're in 5343. Okay, there's 20 different buildings on campus, probably more. Which building is that room number in? We almost always associate the two together. So the problem here is there's a replication between items within tuples. Okay, the room number contains building information. The semester contains year information. There is an overlap, and I will go into precise detail on what the overlap is. This issue, why do I put it first? Obviously, I've got to put something first, but this one is dealt with first very specifically because to solve this issue, we are going to have to adjust the actual attributes within the relation, and all of the other issues that we will address relate to interactions between the attributes in the relations. So until the attributes are fixed, none of the other issues can be addressed. Okay, there can be errors between tuples. So now we'll give an example from outside the text. Let's consider a person relation. There's a name, address, employee number. Now I'm wanting to focus on the address. Street number, street name, municipality, province, postcode. Okay, that's a pretty standard address in Canada. We've got a problem. All of these together determine what the postcode is. The postcode is fixed for a given address. But the postcode determines the municipality and the province. For example, if I tell you that the postcode of an organization is N2L, well, N2L immediately means that's in Waterloo, Ontario. It can't be in Toronto. It can't be in Saskatchewan. It can't be in New Brunswick. We know exactly what it is. So should we remove the postal code, or should we remove the municipality and the province? We don't know. Why would that lead to error between tuples? Well, we could have someone's name, address, the street number, street name, municipality, and we have the postal code, and then we have someone else, maybe a different street number, same street name, but the postal code is different. First of all, we've duplicated the postal code. We've got 2 copies of the postal code, but they're different between the tuples. Maybe someone does N2L3G1 and someone else accidentally does N2L3G2. Maybe a small error, who knows. So the point is we can have error between tuples. And then there's another issue that shows up in this that is caused between tuples, which is the issue of optional attributes and multi-valued attributes. And we've dealt with a little bit at the high-level design with multi-valued attributes, but in fact it'll show up again as potentially causing errors between tuples. Domain correctness. All of the domains in a relational database are pretty primitive. We've got char and varchar and text and int and decimal and variations of them. We might even have something like point, but point is sort of just a 2-dimensional geometry. It doesn't really constrain the thing in any particular way. Let's think about that address issue again. There's a province as an attribute. Well, how do you prevent the misspelling of Ontario? Ontario. What about municipalities? Okay. How do we ensure domain correctness? And I'll be talking about that issue. That's basically solved by a mechanism called attribute lists. But basically, you can think of them as domains, explicit domain information. And we should consider, are there other domains where correctness may be an issue? Salary ranges, for example. Can't really put a domain on salary in quite the same way, but where do you think things like check come from? How do we decide whether or not to put in a check? It's a domain correctness issue. Okay, nulls. I'll have a small section on nulls. First of all, what are nulls? Nulls are missing information. The problem with nulls is they require special coding in applications, they require 3-value logic in database engines, and I'll explain what that 3-value logic is. And sometimes the database has to resort to an assumption because sometimes the database is forced to move from 3-valued logic into a true-false situation. Think of it like, I don't know, a presidential election. In a presidential election, ultimately, you can have as many candidates as you like, but at some point you have to pick a president, okay? In your database scenario, you may have missing information and you say, is x greater than 5? I don't know what the value of x is, so I don't know whether it's greater than 5. And if I say yes, it's greater than 5, then that means it's not less than or equal to 5. So if I say I don't know on that, then I have to say I don't know on the other one also. But at some point, the user gets an answer to a select query. So at some point, these may have to be rendered from I don't know into false or true. So in general, it helps to avoid them if we can. Sometimes they're going to occur regardless, especially in outer joins. And sometimes the performance implications are bad and we're just basically better off to use them. Okay, there may even be space implications that are bad relative to the alternative of having a null. So we will look into that particular issue. Ordered data. Consider a software developer. She, he could be junior developer, senior developer, staff developer, senior technical staff member, distinguished engineer. So imagine your company has a range. Now, whatever level you come in at, you don't jump multiple levels. And there's a relationship between them. A distinguished engineer is higher than an STSM, is higher than staff, is higher than senior, is higher than dev, is higher than junior dev. There's a relationship. How do we capture that? How do we capture that in a detailed design? Is there something in data modeling that is being omitted there? Okay, so I will discuss some of those issues. And to give you an idea that this is not a trivial issue and applies elsewhere, it also applies to things like instruction sequences. Document data. You have a title, a subtitle, an author, sections, subsections. So there's some structure in that data that is ordered structure. And then time series data kind of gets thrown in here, except beware with time series data. Just because something happened before something else doesn't mean it has a relationship to that other thing. So in these cases, there is ordering in this, in this, in this. You should do instruction number 1 before you do instruction number 2, etc. But just because something happened at 8 a.m. and then something else happened at 9 a.m., those are not quite as connected, okay? But there is time series data. And finally, we'll consider other issues, for example, geographic data. Could you add attributes with type point? Yes, but, maybe things can be done better. Streaming data, especially important within the new IoT, Internet of Things, which is basically embedded systems producing data. That data tends to come in the form of stream data. There are other sources of stream data. And any other issues related to detailed design. And that's it for this lecture, just a short one to cover the overview of the topics we'll be discussing.